Hello, in this lecture we are going to know how to install GUI or graphical user interface and how to get molecular orbital pictures, density pictures, graphs for vibrational spectra out of it. So, in this course we are going to use three GUIs. First is Avogadro, second is Chemcraft and third is the ChemiDX. So, let us start with Avogadro. Avogadro is freely available GUI, it is open source also, and it supports a lot of software including Orca, and this is very easy to download and install, and this will help us to prepare our input files. In the previous lecture, when we run our first calculation, we prepared the input file by hand, but now we will see that with GUIs, drawing the structure and preparation of the input file becomes really simplified. So, let us copy this link and we can go to internet. So, here you will see the download button. Remember, we need to download and install Avogadro, not the Avogadro 2, because Avogadro 2 is not compatible with the present version of Orca. So, here it is downloaded and now we can try to install it. I think we have to wait a bit before the download is complete. Yeah, now it is done. So, we will install it. Yes, we agree to the license agreement. You do not add the path in the system path. It will be installed in the C drive. That is where things become most easier, and generally it is a very quick installation. So, now we can type Avogadro here. In some of the cases your background may be black, so you can change the background color from here. In my case it is already white. In case your color is black, you may prefer to change it to some different colors. Now about the tools, here are the available tools. The first one is a building tool. So, let us say if I want to draw methane, this is how it will be built. The next one is the navigation tool, where you can use this one to zoom in and zoom out. The next one is bond centric manipulation tool, but before doing that, let me this one and let me make it a chloroethane. I take it here and so now with this tool I can actually change the dihedral. So, this bond centric manipulation tool, I can select the bond, my bond. Now you see I can, by doing this one, I should be able to rotate it here. You see I can rotate this dihedral by using this bond centric manipulation tool. The next one is to translate the molecule. I can change the molecule's orientation, the center of mass, by using this tool. This one is to select the molecule. So, if I want to have it, select a particular atom and maybe like to delete it, like this I can delete the atom by selecting it. Of course, I am going to undo it. The next one is the auto rotate tool. So, if I select this one, my molecule will automatically start to rotate. Here you see it is now rotating automatically. I want to stop it. Okay, this is if I want to minimize the energy. So, this will minimize using mm force field, in this case it is UFF. Generally it is helpful if you want to get a good geometry, This is where it's actually helpful. And the next one actually is when you measure the angle or the bond length. Let's say for example I want to select this one and I have to support the control 1, and it can automatically give you the measurement of the bond length and the bond angle between the 2 point. And there are many other tools which is present here. You can find about more details about them in the Avogadro documentation page, and you can use this one to create your structure, manipulate your structure to go like this. Before starting our calculations with this, let us also first install the ChemCraft, and then we will come back into Avogadro. We will draw our first molecule, run calculation and try to visualize molecular orbit. So, next thing what we are going to install is called ChemCraft. ChemCraft is a paid program, but you can get a 6-month user free license, so that for the duration of the course you can actually use this software without paying any fee. The advantage of ChemCraft is that it can produce pretty nice graphics. So, if you want to create pictures of the molecular orbital and maybe want to publish for some research work, ChemCraft generally gives publication quality graphics. So, this is where the ChemCraft is. So, I will download and I will download the self installing executable. It is not so large. I want to keep it. Sometimes this download takes a little bit of time, especially the last bit. Yeah, now it's downloaded. So let me run it. Again, we accept the license agreement, the C drive. I want to create a desktop icon, and this is how it's getting installed. So, after a certain amount of time it will get installed, and then we will be ready to use it. We are almost there. Voila. Yeah, the ChemCraft is open. So, it says that either you put the registration key or try. We want to use the free version, so we are going to use it for try. Again, there are many display style available. You can customize any of the style. Generally, what I like to do is to change the background color, so less distracting to my eyes. Good. Now we are all ready to perform our first calculation. So let us clear it. Now let us go to the build tool. We will make a formaldehyde. So, I will start with the carbon, and what I will do is that I will start with this structure. I will not adjust the hydrogen, so I will put oxygen here. I will delete the other hydrogen. Of course, this is not even close to a formaldehyde. So, then what I will do, I will go to the extension, I will optimize the geometry. Let me try to see if it has already come flat or not. this has again has not come to a proper geometry. Maybe we can try to do it in a reverse way. We can clear everything, we go back to here, I go to carbon, this is now the formaldehyde. So, this is an easier way. So, you have to do it trial and error a few times, then you can get to the correct structure, and always you can optimize to get it the structure. Let me, oh no, I do not want to do that. Yes. So, now I have it here. So, my structure is there, now I want to make my first input file. So, you go to this extension, in the below you can find Orca, generate Orca input file, and this will generate an input file for you. You can write a command line, maybe formaldehyde, molecular orbital, and a single point calculation. We are going to use the def2svp basis set. What basis set are, we are going to discuss in the next class, and there are many advanced options. If you want to change the basis set, change the SCF, see the printing options, there are many options possible, like here the printing options are there. Normally if I run this input file, this will not be able to visualize the molecular orbital, because the basis set and the molecular orbital coefficient will not be printed to the output file. This will be saved in one of the Orca files, what is called a GBW file, and we can of course retrieve the molecular orbital from the GBW file. But if we want to get the molecular orbital directly from the output file, then we have to use a keyword here which is called large print. So, this will print all the information necessary for getting the molecular orbital. So, I will now generate the input file. You can click the generate button, you can go to download my NPTEL folder. I will create a new folder called week 2. And the week 2 I will keep the input file name as this. So, now if I go to the NPTEL second week folder, the formaldehyde input file is there. If you really want to see what is there, this is how the input file look like, and this is my comment statement what was given. Now, let me try to run it. So, I will right click here, open in terminal, my Windows PowerShell is opening. So, the way we run is space greater than this calculation is running, and the moment your calculation is done, your prompt should come back. So, once your calculation is successfully done, you will not have any of this temporary file which you will see while running. So, we will have files like output file, density file, GBW files, and the text file. So, this output file we need to open in a GUI. In our case, we are going to open it in a GameCraft, But before going that, let us open the output file using Notepad. So, these things we already discussed what they are. This is the formaldehyde coordinates, and this is the basis set what we are using, and it has 38 basis function. And total number of electron is 16. So, this is where the initial gas orbitals, initial gas has been done for the Hartree-Fock. We have discussed about the steps involved in the Hartree-Fock. One of the first step is to calculate the integrals and do the gas for the Fock matrix. Once you have that, you solve it iteratively, you see the energy is changing at each iteration, and it is actually coming down 75, 77, and here it is converged, and once it is converged, this is my orbital energies are. So, up to 7 there are occupied orbitals. Remember, although there are 16 electron in the counting, Orca is written in C. So, the counting actually starts from 0. So, it is 0 to 7, total 8 orbitals, and this is your what is your HOMO, highest occupied molecular orbital, and this is your LUMO. So, you see the gap between the HOMO and LUMO, it is 15 electron volt. Whenever this gap is small, it says that this molecule is not a single reference, this wave function is not a single reference wave function. So, Hartree-Fock may not be a good description in that case. You need to do something else in these cases, and we can discuss more about it. But here at least you will see there is a 15 electron volt separation. So, Hartree-Fock here is a good option in these cases. So, here it prints the molecular orbital which you will visualize with the GUI, and once this printing is done, what I want to show you is the population. Here are the Mulliken population analysis. Now, you see the oxygen has a partial negative charge which we expect, and the carbon has a partial positive charge, and the total sum of course all the charges is 0 because it is a neutral molecule. Similarly, after the Mulliken, it also prints the Loudon charges. We have discussed that the population analysis is not unique, you can have it in multiple ways, and this is how the Loudon charges looks like. So, the oxygen is still negative and the carbon is positive, here the hydrogen also gets a slight negative charge. And the other important thing is somewhere there should be a bond order printed. Here is the Mayer bond order. Now, you see. So, the first one is between oxygen and carbon, the bond order is almost close to 2. We know it is a double bond. Carbon and hydrogen bond order is close to 1. So, we know it is a single bond. So, the Mayer bond order analysis gives you an idea about what kind of bonding it is doing. This is where my final HCF energy is getting printed. And this is my total dipole moment. So, my total dipole moment is in the magnitude is 2.85. Now, let us open this output file in the GUI Chemcraft, and then we can see a lot of interesting thing. So, I go there, click on the open button, and I go to the NPTEL week 2, I open the output file. And this is the output file looks like. So, there are various tools there. This comes to single point geometry, and here is the option, it says source dipole moment. So, this gives us the direction of the dipole moment. Here you can see the dipole moment is from towards the oxygen to the carbon. We knew the oxygen was negative and carbon was positive. So, the dipole moment direction is towards carbon. Now, to visualize the molecular orbitals, we need to go to tools and orbitals and render molecular orbitals. So, here is actually we have all the molecular orbitals. In principle, we can visualize all of them, But in this case, what we are going to do, we are only going to see just the HOMO and LUMO. So, we select both of them, we click OK, and this the HOMO LUMO comes here. Now, let us see one by one. So, this is my HOMO, it says it's occupancy 2. So, now to see that, we need to show the ISO surface and we need both the surface. Remember, here one surface is plus, one surface is minus. This plus and minus is nothing to do with charge, but these are phase factors. Let me reduce the zoom a little bit so it looks good. Yeah. Now, we have to look at the contour values. Remember, these are, although we call it an orbital, it's a constant probability surface, and the contour value denotes how much portion of the probability is outside these surfaces. So, if I reduce this value, my orbital size will increase, and if I increase these values, my orbital size will decrease. So, remember, the size of the orbital does not denote actually anything, because it depends upon what kind of contour value you are using. There are various ways to measure what kind of contour value you should use, but generally a good idea is to, if you are drawing molecular orbital and comparing them, it's generally a good idea to draw all the molecular orbital with the constant ISO value. So, this is the molecular orbital for the HOMO, its occupancy 2, and for the LUMO it looks like this. You see, we have to rotate it. So, the plane of the orbitals, the plane of the nodes are slightly different. So, this is how this molecular orbitals in these cases actually are going to look like, and if you really want to, there is an option where it gives the best view. I believe this is the one, or you can manipulate the view like this by rotating like this and then adjusting the zoom. And if you want to save the picture, you can always save a picture in this format in case you are interested to save the picture for some kind of a molecular orbital. This is how you go, copy there. If you click OK, it should get you saved. Now, this is how the molecular orbitals of this formaldehyde looks like. In principle, you can generate the molecular orbital of anything. Now, let us go to this question. So, this was formaldehyde. What about acetone? If I replace the two hydrogens of the formaldehyde by a methyl group, it will lead to acetone. Question is that, can you compare the energy of the dipole moments of the acetone, or for example any properties? Before dwelling into this answer, let us first draw the structure of the acetone and then run a ORCA calculation on the top of it. I will request you to stop the video at this point and draw the structure yourself, so that you also get some experience on drawing the structure and run the calculation, and maybe after you are done, you can again resume the video and see what I have done, so that we can compare our notes. So, let us go to Avogadro. This was my formaldehyde. So, what I will do is that I will again go to the carbon now to make it a single bond, and I will click here to make it an acetone. Of course, I will again optimize the geometry. So, now this will look like, this is no longer formaldehyde. Of course, we are not going to visualize the molecular orbital here. So, I may skip the large print option. Remember, the large printing will put too many output files, too many material into your output files. So, the size of the output file can increase, which will take more space and may be more difficult to open if you are dealing with much larger molecules. Now, let us generate this one. I come to the same folder, I write acetone, I save it here. Now, while this calculation runs, you will see a lot of these temporary files will get generated. And even after your job is done, if this temporary files does not get automatically removed, that means your calculation has not been completed properly. If your calculation is completed properly, then these temporary files are supposed to get removed. And this is one of the things to notice, is that is your temporary files are clean or not, because these temporary files are often quite large, and if it does not get removed, it can actually create a lot of this disk space. It may get filled pretty quickly. So while you run this calculation, make sure you run this calculation on a drive which has sufficient space, because although the output and the input file actually has a very small size, this temporary file can actually take a large amount of space, and this can actually make things difficult. Now, here the calculation has been done. I can go to the end, because what I am interested in is towards the end. Here is the dipole moment dimension, and here is the dimension of the total energy. Let me copy this one, and I also want to see my dipole moment. I also had the output file for formaldehyde, so I can get this values for formaldehyde also. Here is the value for the formaldehyde single point energy. And the dipole moment. So you see that both the energies of formaldehyde and the dipole moment is actually smaller. Energies is small because formaldehyde has less number of atoms than acetone, and the reason why the dipole moment is small, you can find it actually in the output file. There is a signature of it, why it's small. Let us go to the population analysis on the top. Let us see the Mulliken one. So sometimes, as I told, if you give the large print option, it prints so many data in the file that many of the important things what you want to get access to get suppressed. Because of this, it becomes more difficult to find it out. So if you do not need the molecular orbital, don't use the large print option. This is Loudin. Again, this will be, we are going up towards the Mulliken. here is the molecular charges. Now you see, in addition to the oxygen, also this carbon now has, these two carbons now also has two negative charges. These are the methyl carbons. Now because now I have a higher positive and negative separation, this will lead to larger dipole moment, and if you really want to see it again, the direction of the dipole moment, I can open it and I can open the acetone output file. And if you do the single point calculation, the direction remains same, but the magnitude is slightly increased. So just think about it, can the energy and the dipole moment of these two molecules will be comparable or not? We will come to this answer and we will discuss it.